That's the next thing. Happy Garbage Day. Happy Tuesday. Welcome back to class. Week 3 already. Almost at the end of January. Just one more crappy month to go in terms of Iowa weather. I feel like February is the worst. Once you get past that, then we have a little bit of outlook that's a little better. So this morning, I looked at your Homework 1 effort drafts. I did not read them carefully yet. I looked to see that every question had been attempted, and if you attempted every question, you got your 5 points for trying. The idea was to make you start to think about these things in a greater level of detail. That way, when we talk about it as a group, everyone has at least some answer that they wrote down to share, and we can talk about why other things that could be added to the answer. So I will, as I had said in the instructions, I'm not planning on providing any specific feedback to your effort drafts in writing. However, during our discussion, if you'd like to say, this is what I wrote, can you tell me if this is okay? Then everybody gets the feedback at the same time, and that's a more fair experience. I will provide feedback on the accuracy drafts that are due in a couple of weeks. The next thing that you have to do is your first formative assessment. I turned that on this morning. That is over this topic of accelerated time models. The last question, of course, theme song question, my favorite one. So start thinking about what you'd like your theme song to be. Otherwise known as walk-up music. Apparently that is a synonym. That's a more sports-centric thing. So the other class gave me a lot of theme songs that I would not call walk-up music. They're a little more like chill. But if you want to give me chill, that's fine too. I can work with it. Theme song can be whatever it feels like to be. I have mine. I've got mine picked out, but I'm going to save it till next week. So the next thing after that you'll have is homework 2, which is going to be a canned data exercise based on this topic as well. So using our SAS data to fit the same types of models, but adding time invariant predictors to examine cohort effects. I aim to have that available to you by the end of this week so that you'll have a week to 10 days to go through everything. I'm waiting to see how far we get with this and then the discussion about homework 1 before I post new stuff, because I may have to juggle things around a bit if we get too far off track. So, all right, I think that's all the housekeeping stuff I have. Anything I'm forgetting or questions about logistics, due dates, what you're working on? No? We're good? Good enough? Anyway? Did you shut the email down so it doesn't bother you?
Oh, yeah.
Okay, good. Good, yeah, because
yeah.
the blinking, like the notification thing, and especially like just seeing the one there, like I don't know what it is, but if I don't check, it's going to bother me. Like that, like mentally, I can't handle that. So I turn everything off so that you have my undivided attention. It's much better that way. It's much more fun. And quite frankly, we need all of the attention we can get to get through this topic. This is one of the trickier things that I have to tell you about. So it does get better with exposure and practice. So I just want to preface this by saying that this is your first situation in which you're faced with this task of trying to think about what it means to have a level 1 predictor, a time-varying predictor, and have part of its information be between persons and part of it be within persons. This is the first time you've seen something like this. And so we will have many more examples in addressing that type of situation throughout the semester. So what are we talking about very broadly? Do you remember this topic? Yes, maybe? Tell me some words or gestures, letters that come to mind. What are we talking about? Smushing. Yes. So otherwise known as what? What would people who are not me talk about smushing? What does it mean?
Conflated effect?
Yeah, putting the between and within together, conflated. Yes, the idea of contextual effects is also relevant in this. But in this specific context, it's the idea that if you're sampling people of different points in time and you're trying to align them all onto the same trajectory, that's an assumption that you're making, that they align. I used to say align up because I would change my mind halfway through the sentence as to what I wanted to say, and someone pointed out you can't say align up. You can say line up or you can say align, but you cannot say align up. So We're seeing if people of different age cohorts align, and if they do, then that would be evidence that smushing is okay. So it is an empirical question as to whether the between-person information and the within-person information in a predictor are going to tell you the same thing about an outcome. It's more tenuous and less likely to hold the further you're trying to stretch across your cohorts. So the wider the range of time at baseline, the harder this is going to be to work. All right. Yeah, those are the big pictures. When do we need to worry about this?
Accelerated design.
Accelerated designs. Whenever people differ in time when they walk in the door. When you're sampling people on different points of their journey, so to speak. Can I say journey? I sound like a YouTuber or something. You know. My journey. Yeah, we're all on a journey. Some of us older than others on that journey, decidedly. All right, so we started this example last time, but should we go back over the data setup? Would that be helpful? Okay. Because this is where, like, things that sound like they would be the same, like age and time, are not the same. And so, like, understanding what the variables are is going to be important to understanding what their effects become in the models. So I have time as one version of my level 1 predictor. So level 1 meaning time-varying information. Time is a time-varying predictor. And the way it's computed is time-varying age minus age at time 0, or baseline. I think in the slides it's T1 for like the first occasion, but technically since time 0 is like 0, it doesn't start at 1, it starts at 0. I'm going with T0 for this. I also made a squared version of the variable because the formulas get really ugly in terms of the syntax when you have to have interaction terms and squared terms of interaction terms. So I have the squared version made explicitly. I have rounded versions of occasion, so year in study, and of age, so that I could make some pictures. I then also have the age variables, where I have time-varying age 84, which is a level 1 predictor centered at a constant instead. So we're changing the definition such that the intercept will be someone who's 84 years old, but otherwise that variable still contains differences in age that were there to begin with, and differences in age that became there over the longitudinal sampling. So the effect of getting older and the effect of being older as two separate pieces of information that this variable still contains. Then we have the squared version. Then we have age at T0 84 is the way I would say that. This is a time invariant predictor. This is level 2. So this is your age cohort, so to speak. It would be birth year would make the most sense in studies that span multiple years, but because everybody was started in the same year, we can just do the age at which they started. And this is also centered at 84. You don't have to center at the same place, but it makes some of the translation a little bit easier. Okay, and same thing with the R code. I think you've seen all of this stuff before. Any questions about how to make the variables or what they mean yet? Okay, so to recap, we're going to examine two different level 1 predictors. There's time, which is purely within, and there's time varying age, which is a mixture of between and within. At level 2, we have baseline age as the only predictor in either set of models. And it only contains between level information because it's level 2, like that's the definition. No, I'm not trying to be like flip with that. It's like a level 2 predictor is between only, whereas a level 1 predictor is not necessarily within only. It's within and between. That's what makes it tricky. Okay. So then we looked at descriptive statistics for the story. We have recall as a measure of, as our outcome variable. These are real data, by the way. I got permission to use them. I may have doctored them a little bit to make a story, but they are otherwise real. So this outcome ranges from 0 to 16. And time and baseline age are negatively correlated. So I have a disclaimer here that we can't talk about between versus within as orthogonal constructs in the way that you can if you use a person's mean age, but we can talk about cross-sectional age and longitudinal age. I feel like that's a fair thing to say. So then we had empty models. For first one is for age as an outcome. Now that's a little weird. Why am I doing this?
To figure out what proportion of the variance is from between.
Yes, I'm doing this to figure out how much of the variation in time varying age is actually between persons, cross-sectional age variation, as opposed to longitudinal within person variation. I don't have the centered version of age here, so the intercept would be the mean for this variable. If I had the centered version where I had subtracted 84, would that change the variance components any? It would not. It would just move over what the fixed intercept would be for age as its mean. So my variance components then, this is stata output first. So that is variance of the constant, otherwise known as what?
Random intercept.
Yeah, that's my random intercept U0 variance in age. Var residual, what's that? What's the other one? Yeah, E variance at level 1. Yep. So the interclass correlation is computed, here's the formula. Intercept variance over intercept plus residual variance works out to be about 40%. So 40% of age is cross-sectional age differences. We know that that is significant. SAS and Stata both print out this test without us asking for it. LR, can you guess what that stands for? Yes, it is. LR test versus linear model. Now, this is a bad way of labeling it, in my opinion, because these are all linear models in the sense that they are slope times variable plus slope times variable. What do they mean by that? Without the random intercept. So I would say this is versus single level model or versus like regression model or something, but linear model is not a specific enough term. But no one asked me, so this is what it says. And again, if all of this output were crystal clear, I would not have a job, so I'm kind of okay with it. Chi-bar. So this is the likelihood ratio test statistic. This is the difference in -2 log likelihood between a model that has the random intercept variance and one that does not. What the chi-bar is referring to rather than chi-square is related to the fact that there's a 0 and a 1 in here. What this is doing is saying this p-value is based on a mixture distribution, where mixture chi-squares are used anytime that you're adding a term where the null hypothesis is on the boundary of what it can possibly be. They say it's on the boundary of the parameter space. Meaning, what's the smallest random intercept variance you can have? 0. What am I testing with my null hypothesis? That it's 0. So that's the problem. So the 0 in here for the degrees of freedom would be all the times that a sampling distribution for it would want to go negative, like around 0, but it can't. So functionally speaking, whenever we're testing whether we need a random intercept and it's only the one thing that you're adding to the model, you can take your regular p-value and cut it in half. The critical value for whether it helps the model becomes 2.71 rather than 3.84. So only when it's between those two numbers do you need to care about such thing. But I pointed out because this is the way the output is labeled differently when it provides a mixture chi-square p-value versus a standard one. Here is the corresponding Elmer output. And we're using Elmer throughout this example because the R matrix has no covariance pattern and it's diagonal. So I'm not doing anything with respect to changing the variance of the E residuals or their covariance over time. Fortunately, we get the agreement in the numbers here. That's always nice when that happens. And interclass correlation is the same. Did the same thing for time, this is actually sort of a stupid thing to do, but I was trying to prove a point. What point am I proving if I model time as an outcome?
Time is really within.
Time is within, so if it is purely within, I should get 0 for my intercept variance, and indeed it's 0 to like 20 decimal places. And the chi-square for adding it is 0. So this is just a proof of concept, as they say, that yes, there is no interclass correlation for time as a level 1 predictor. That means it's all within or all between?
All within.
All within. So the fact that it has within person information, longitudinal information, is a logical prerequisite to that information being related to that of an outcome. You have to have variance before you can have covariance. But because time doesn't have any cross-sectional variation, it doesn't have between person variation in this intercept, that means it logically cannot have a between person effect. Between persons, it is a constant, not a variable. So this is an important, conceptual thing here. A predictor has to have variability at a given level before it can have a slope relating that variability to an outcome at that same level. If it doesn't have variance, you don't have to worry about this. So this is the reason, in part, why all of the examples last semester had time where it was perfectly balanced with no between information, because then it was simplified in terms of what it could possibly do, and I didn't have to talk about all this. Likewise, time invariant predictors is purely between. They don't have within-person information. There's no way they can have a within-person effect unless they interact with a within-person variable or something. But on their own, they cannot. So R agrees that there's no intercept variance, and the ICC is not 0, it's just NA. Okay, whatever that means. All right, empty model for recall then. Same idea, but this is the outcome that we care about. So on average, recall is about 10. The interclass correlation for it is higher than the others, so 67%. So that means if you want to predict who does better on this recall test, it's more important to have level 2 predictors or level 1?
Level
2. Time invariant. 67% of this is because of person mean differences, according to this model. And then our output, just to remind you, I'm adding a couple pieces here. This function first spits out this right here so that you have enough decimal places to feed this into the homework system. So the log likelihood for the model times -2 is this deviance thing here. Then we get the variance component solution, fixed effects, and interclass correlation. Then we looked at pictures of the means. So I fed in rounded age and rounded time into Stata to make these pictures. I did the same thing in R by treating those two variables as factor variables within the equation. And the point of that is just to get a sense of what the trajectory is that the fixed effects are going to try to recover. Like this is what, when you put in age or time as a predictor, this one's age, this one's time, this is what it's trying to do. So even if you don't have balanced time, just to make the picture, rounding things just to get a sense of what the trajectory looks like can be helpful. And in particular, looking at the width of the confidence intervals around these points can give you a sense as to which points maybe are just so noisy that you shouldn't worry about them looking a little weird. Like 79 is much higher, but we have no idea what this mean is. Like there's very few people who contributed to this data point. So it's relatively less important to fit it well than the ones that have more information. Okay, and I think that's about where we left off. Does that sound about right? Okay, any questions before we get to some new models then? Age and time-a-palooza, as it were. Okay, Zoomers, no questions? I saw some thumbs. All right. So I'm trying to use color here to help us keep track of what we're staring at, and then also this ties to the slides. So in the slides, I use this blue for age and green for time. Question?
I think I'm getting a little lost in the trees and I can't see the forest.
Okay.
Big picture.
Big picture.
Like, what is it we're trying to do?
What are we trying to do?
With this.
Okay. I am showing you, the big picture is that I want you to see how to interpret these fixed effects when they are multiplying age versus time, and how the interpretation changes as a function of whether you've controlled for age at baseline or not.
Great. Thank you.
Does that help?
Yep.
Okay, good. Thanks for the comment. The forest is just as important as the trees. If you don't have the forest, you don't know where to put the trees, like to hang the information on. So it's good to keep the big picture here. So would I do all of these models this way in practice? Not necessarily. I'm trying to demonstrate what happens, and so that requires a little bit different sequencing for this example. I have a paragraph about that. I wrote it out. Okay, so I have added in the next step here to my empty model for recall 2 level 1 predictors, age TI, so that means it's time varying. So if your equation is right, every variable that goes in level 1 should have a TI subscript. If it should have an I, it don't go in level 1, it goes in level 2. So I have age as a linear slope and then a quadratic slope of age, and I did that because this looked kind of quadratic-y to me. I left only a random intercept in the model for the variance though. So beta 1 and beta 2 are just fixed effects thus far. So this model would say the trajectory is curvilinear, but it's the same curvilinear for everybody. People differ in their intercept. So it's a parallel trajectory that we're fitting. So to do that, here's the 2 programs here. I think from this point out, I'm only showing our output because you've all seen Stata output before and you know what to do with it if you want to use that package. SAS output is inside the download folder as well if you want to look at that. So we have C dot for time varying age and its squared version. Right here is where the intercept is assumed to be because Stata has that by default. We're in maximum likelihood so that we can contrast any model that we want to. I'm storing the information from this model because I'm going to do a likelihood ratio test subsequently. I'm also making predicted outcomes so that I can generate a total R square to talk about variance explained relative to an empty model. So how much variability does time varying age explain through its linear and quadratic slopes? That's what I'll want to know. Question?
You are studying a fit RIH there in the estimates line in Stata? Yes, that
This?
object.
This line?
But you have not defined that object before. That can be any label or name?
So yeah, this part is dedicated Stata code. This is a name I made up.
Okay, so we can change it without problem.
I believe so, as long as it follows the naming conventions of variables, like it can't have spaces or special characters, I don't think.
Okay.
Nikki, does that sound right?
Yeah.
You're nodding?
But
Okay.
to your point, you don't have to define it beforehand and then call it. Like, this is essentially being like, create this object and put the
With this
estimates.
name. Okay, cool. Thank you.
And so then,
That's why I get confused in R.
Yeah, exactly.
yeah, so then this name refers to the estimates being saved. It's kind of like a model object in R, but I think
Yeah.
it's more specific.
Okay.
That's one thing that I'm not good at that I need to work on if I wanted to do more in Stata is like how to access saved information so that you don't have to like type in hand calculations and make it do it. I'm not as good with that. I just know that if you call, like there's E and there's another one that if you call it right after, like it will spit out whatever just happened.
Yeah.
So like this is a saved object and I'm making it calculate -2 times that log likelihood and then it will display means print. So, all right.
And yeah, in the case of the sample size, there you have 207.
Yes.
We must put that number manually?
Yes.
Okay.
If you want so the BIC is the problem because the BIC is a function of log n, and different programs have a different definition as to whether it should be level 2n or combined level 1 and level 2n. And to keep it the same, because at least when SAS does level 2n, and I think that's more common, I told it to do that specifically. That's less of interest if you're not going to use AIC and BAC to compare things. But I want stuff to match across packages as much as I can. This column right here, that's this pred age, that is going to be a variable in the analysis data set that gets added to it. And so if you already have a variable called that, it will yell at you and not let you do it. So you'd have to like either re-import the data or go in and manually delete the column and then it will put it back. So it's kind of clunky that way. The Zoomers are dropping internet. No worries, Zoomers. Just ring the doorbell and I'll let you back in. See, the difference between teaching here on Zoom and teaching at home on Zoom is that we all get to hear the doorbell. It's not just in my headphones this time, so it's all good. All right, yeah, so then I am using ML instead of REML so that I can compare across any kind of models with respect to the mean side or the variance side. Just a random intercept to start with, so I have 3 fixed effects in this model. All right, so we have then my random intercept variance and my residual variance from before, and it tells me how many observations I have, which is nice. We'll talk about variance explained in these in just a second. Here's my fixed effects. Okay, so age time varying is what's in the model right now. So who is my intercept for?
A person at age 84?
A person at age 84. So this is not at the beginning of 84 or at the middle of 84, just 84. So if you started the study at 80 and you only went until you were 82 and you didn't come back, like this is the predicted outcome for you still, like when you would get to be 84. Or if you started the study at 86, this is still your predicted outcome at 84. So regardless of where you're joining the trajectory, this is one trajectory according to this model. So an 84-year-old has an expected prose recall of 9.8. Okay. Now this one. What's this one mean? The linear effect of time varying age.
Oh, is that for each year increase in age past 84, the outcome decreases by negative 0.12, roughly?
So for every year older than 84, the outcome decreases by 0.12. I can't end my sentence yet, though.
Because then we also have the quadratic term,
So this
which is twice the 0.004 that needs to be added for each year.
It does, but this is conditional because of the quadratic. So this is the linear slope at 84 specifically because the line is bendy. Yeah.
Oh, is this where, when we talked last semester about you take the highest order and then everything underneath that is at baseline, right?
Yep. Another way of saying it is that time varying age squared is a two-way interaction. So the main effect is conditional on the interacting predictor being 0. So this main effect is conditional on age being 0 at 84. So yes, this is the instantaneous linear slope, or the first derivative of the function with respect to age at 84. Math people, did I say that right?
That sounds right.
Does that sound right?
That
Right
sounds
enough?
right, yeah.
Okay. I feel about as comfortable speaking calculus as I do speaking German. So I always want to check. Jonathan makes fun of me whenever I try to speak German, because apparently it doesn't go well. But I know like 6 words, so that's all you need to get there.
Can you say that interpretation again?
Yes, I can. So this is a linear slope. So for every year older, your outcome goes down, given that it's negative, by 0.12. But this is the rate as evaluated at age 84 specifically, because of this higher order quadratic, which is age times age. So if I have my picture, here's 84. It's the slope like at that point specifically, because the model implies that it would change as time goes on. The quadratic implies that the linear slope changes. Okay, does that help?
Wait, can you differentiate between at 84 versus at time 0? Is it both?
Time 0 is not in the story.
Okay.
It's age 84, because time is not in this model as such. Like, so time varying age is a mixture of time and baseline age, is another way to think about it. Okay, question, Zoomers?
So the negative 0.118 is the slope at 84.
It is. Yep, it's at 84. Instantaneously. It is the slope of the line tangent to the curve. That sound right?
Yes, that is right.
I
Yeah.
Yes.
think so, yeah.
Oh, goodness. I used to be really, really good at math. I never had a problem with it. I just stopped taking it because I didn't think it was necessary and it wasn't interesting to me. And now I regret that. So I'm working on it though. Okay. So as people get older, the score comes down, is sort of the story at this point. However, what does the quadratic do to the linear slope? You got 4 choices, as usual. Which
Less-
combo?
Less negative.
Less
but
negative.
not significantly
Yeah.
less negative.
Slowing it down. Yep. By how much does the linear slope slow down per year of age?
Twice the
Twice.
slope.
Yes. So we have a question from the Zoomers. For examinees at age 84, 1 year later, their outcomes will decrease by 0.12. Is that right? Not exactly, because it's at that point. So I know that's a weird thing to think about a rate of change for a dot, but that is what it means. Because the second you move off that point, the slope changes. So it's at that point. But yes, twice the quadratic is how much the linear slope slows down per year. So at age 85, it would be 2 times this number plus 2 times that number, so making this overall less negative. So a U this way for you guys. There we go. Coming down, but that
Lisa, I have a question.
Yeah.
So can you remind me what the outcome is again?
Prose recall. It's a memory
Okay.
test. Number correct, I think.
So something that I'm kind of struggling with, because obviously since it's quadratic, we're going to see, it would imply that there's going to be an increase eventually. I mean, probably not until someone's like 120 or whatever, but
Yes.
so, but if we're in if it is a case where maybe it isn't outlandish to have like, 30 units, it's like if somebody could live to 120, whatever. Is there a way to address that increase eventually, or like if the theory doesn't support that necessarily?
Yeah, you wouldn't want to fit a straight up quadratic model. You'd want to fit something that would imply that it levels off and doesn't come back up, or
Okay.
like a piecewise model where you're trying to find where the knot is, where the curve stops and like a straight line begins, something like that.
Okay.
My interest in fitting this is because in cognitive aging and in a lot of developmental contexts, like quadratic models are very common still. And I think the extensions as to how the problem of smushing or convergence applies when you have a more complex function is not as frequently explained. It's almost always explained in the straight linear main effects case. So I wanted to expose you to the same concepts apply no matter how complex your function is. But you're right in that theoretically, this predicts that eventually people will come back up the other side, which, to be honest, if you look at the picture, kind of happens. It does happen that they start getting better again. Now, however, that is almost certain an artifact. Who is still alive to contribute data at 95? Not a random subsample of the people who started over here at 79. So this overall trajectory is describing different batches of people. And I think that's why we see this sort of weird uptick at the end. But the model doesn't care. The model fits it just fine. Okay. So these coefficients then are assuming that this is your trajectory regardless of when you join the trajectory. Age convergence, or that there's no contextual effects of age cohort, that smushing is okay, that conflation is okay. All of those are synonyms to describe the same issue. Question?
So I'm trying to remember from our last lecture in chapter 10, the way that because this model is grand mean centered.
Yeah, constant centered, I would say. Yes.
So the way that you save this model is by adding the baseline age for each person
Yes.
as a level 2, correct?
That's what will happen in like 3 pages or something. Yep, level 2 age is going to come in. Nope, that's good that you're anticipating it. That is how you save it. Because this model is making an untested assumption that there's no, basically that the effects of cross-sectional age differences between different people have the same pattern as longitudinal age changes within people. That's what this is saying. How well does this model explain variability in recall? Here's your R square, 0.5%. So not very, in terms of effect size here, not very impressive. And in fact, the quadratic is actually not significant. I'm keeping it though for demonstration purposes. Okay. So that's one way of doing it. Now what if you didn't want to make that assumption, that everybody is on the same trajectory? What if you just want to focus on the trajectories that are observed for each person during the study? Then I would use time instead of age as my level 1 predictor. So I'm calling this time, but I am deliberately showing the centering in the equation to remind you of how that was constructed. So time varying age minus age at baseline. So age TI versus age I. So we are subtracting off the cross-sectional information here. We are removing it. So what's left should be longitudinal only, not exactly completely within persons, but for all intents and purposes, we can say it that way.
Hold on, I'm digesting.
Yep. So by removing baseline age, what's left for time varying age should be predominantly within person longitudinal information.
Lisa?
Yeah.
So this is analogous to use the person mean center option, right?
It is analogous, but the fact that this is only one occasion and not the mean is why it's not a complete between within separation. You'd have to use the person mean to make it a complete separation.
Okay, yeah. So could we use, instead of the age at the beginning, the time at the age at the end? Because we will have the same number of time points, right?
If you could, if it weren't the case that most people had dropped out by then. That's the problem.
Yeah.
Because by definition, everyone has a time 0. Like, that's the first time we measured you, like however old you were. Not everybody has a time 8. And what happens to cases that have missing time invariant predictors in these models?
Time invariant, they get dropped.
Yeah, the whole case gets dropped, listwise deletion, because they'd be missing something from every single row where an occasion is a row. So yeah, that's why. And I'm not using mean age because mean age is biased by missing data as well. Because if 2 people started at the same age, but one person kept going longer, their mean age would be older, which is not the same. So I'm trying to go for cohort as a pure representation of level 2 variability here. So the only difference then in the code is just the variables that you're sticking into the fixed effects. This is time and time squared rather than time varying age and age squared. So then in the output, the fixed intercept is now not for whom, but for when.
At time 0.
Time 0. Doesn't matter how old you are. Time 0. First time I saw you. Now we have a different pattern of quadratic. This is interesting. What does the linear effect of time tell us?
People improve their performance.
They're going up. But that's when?
At the beginning of the study.
At time 0. Again, instantaneous because of time squared. So
Whether we're dealing with time, it's time 0.
it is time 0.
Center, right?
Yep. We don't know what age they are. We know this is the first time we saw them. Let me go back to the picture for a second. Yeah. A little bit positive to start with. And then things take over.
The way we created the time variable, though, it's still, would a 1 unit increase be a year?
Yes.
Okay.
Yeah, everything's in years for this.
Great.
Yep. Yeah, I would keep these on the same scale as much as possible. So yes. So one of the potential reasons, by the way, and this is the criticism that people use against using these models, is that this does not represent aging, it represents practice. Because every time you do something, you get a little bit better at it, right? But at the same time, these people are getting a little older. So how much of this is because of, I've done this test before, now I'm better at it, versus I'm older than I used to be? As long as the second time you do a test, you are older within persons, that is a confound that cannot be solved. There's no way that you can use a model to fix that. I'll say that again. I see you looking at the ceiling, right? That's what I do, and it's like, wait, I can't take any more visual stimuli until that processes. So long as the second time they do a test, they've seen it before and they're older at the same time within persons, that's confounded. What you would need to do is have them practice this like over a week or something like that, to where you can get a pure examination of how much is improvement because of practice, because you're not going to age in a week. Most of the time, you know. Unless you're like going through comprehensive exams or, you know, something like that, that might age you in a week. Am I right? Yeah, or, you know, like giving birth or something, that'll age you really quick. All those fun things. All right, so people are going up initially, and then what happens as time goes on? What's the quadratic doing to it? Which pattern is this? Yeah, less positive. So it's bringing it down and sending it back over the other side of the U. So this means that for every year further in the study, at time 0, they improve by 2.6. But then per additional year in the study, that positive rate of change slows down by 0.09-ish, twice the quadratic. Same thing here. So these two variables, though, are purely longitudinal. It's just talking about the trajectory that you have regardless of when you started the study. It explains actually a little more variance than age did. Not much. Now here is my, this is an Excel table I made so that I could show them both at the same time. Relative to the empty model, the two fixed effects in the age model explained 1.8% of the residual variance, and it made the intercept variance go up a little bit. That's going to happen anytime you explain residual. The time model explained 3.5% of the residual. It actually did better. And that larger reduction in the level 1 variance in turn caused a larger increase in the level 2 variance. So at this point, the models are not equivalent. You don't end up with the same variance components and the same reductions in variance. And I didn't emphasize this, but you don't end up with the same likelihood either. So these are different models at this point. The difference between them is that the age model assumes that age differences have the same impact as age changes, whereas the time model does not make that assumption. It's just time changes when you're older. Okay. With me so far? So from this point forward, I would normally do random slopes, and then I would go and maybe like do level 2 stuff. I'm skipping the random slopes for right now so that I can show you how adding baseline age makes the models equivalent once you've unsmushed all of the pieces of the trajectory. Then we'll look at the random slopes and see what happens. So I'm adding a moderator, a level 2 time invariant predictor of age at baseline minus 84. So the red is the new part then. So I added 3 different terms.
So
And
we're back to the age model.
we're back to the age model,
Okay.
then we're going back to the time model.
Great.
Okay. We have a question, what's the difference between a nesting effect and a contextual effect? I'm not sure what you mean by the question. Do you want to clarify? And I'll reload my caffeine. See, I'm not sun-kissed today. I've already had my allotment, so. This is somewhere like half as much as Diet Mountain Dew. Nesting and multi-level. Contextual effects are something to be concerned about regardless of what your levels mean. So in October, we'll be having this exact same conversation. If you come to the clustered multi-level class, those of you who haven't had it yet, we'll be having this conversation, except rather than between and within person, it'll be between and within group. Yep. I could talk about this from a strictly this is level 1 versus level 2 point of view, but I feel like that's a lot harder to hang on to when the levels don't mean anything. Like, to talk about levels generically at first is I found to be very tricky, very hard. So we're back to the age model, and then we'll do the time model. Okay, question?
Yes, in this case, those red terms in the intercept would be contextual effects.
Yes.
And in the slope, given that we do not have a random slope yet, that could be a systematically varying effect.
Yes.
Okay.
Yes, so contextual effects here is the key idea, is that we are actually testing whether smushing is okay. So each of these 3 new effects of baseline age has a job to do. The linear effect of time varying age is going to be fixed by this linear effect of baseline age. So these two, like the effect of time varying age is a mixture of cross-sectional and longitudinal. I'm throwing this into control for cross-sectional, so what it should have left is strictly longitudinal. Likewise, quadratic age is in here because of this term. So quadratic time varying age gets unsmushed with quadratic baseline age. And this cross-level interaction is also necessary to unsmush, I think it's this one, if I remember correctly. I have to go back and look at my math, but I know that all 3 of these are necessary to make the model equivalent, to fully disaggregate cross-sectional versus longitudinal. But your question then, Vladimir, this right now, the linear effect of time varying age, I would call that systematically varying because it's allowed to vary as a function of baseline age, but not randomly otherwise. Whereas the quadratic age slope is unmoderated, it's just fixed. It's the same for everybody. So the intercept is random because I've got the U here. The linear age slope is systematically varying, and the quadratic age slope is fixed. So we've got all 3 kinds just exemplified in this model. So chapter 10 and the other book chapter that I wrote gives you the algebra as to why it has to be this way. I'm less interested that you know that other than just the concept of each of these things needs to have the cross-sectional part controlled for so that it can become the purely longitudinal part. And if it's okay to smush, if everybody just joins the trajectory and it's all lined up, then these things shouldn't have anything left to do. Shouldn't matter when you join the trajectory. So that's what we're testing empirically. Is everybody aligned onto the same trajectory or not? Okay. Questions or any of that you want me to repeat?
So,
Yes.
Is that just they're not significant, like from the fixed effects, or I'm sorry, what do you mean by that? If they don't do anything, they're not have anything. What are we going to be looking for in our output eventually?
If these slopes are non-significant, then this overall trajectory is good enough. It doesn't matter when you joined it. That's evidence of age convergence, or that smushing everybody onto the same quadratic trajectory is okay, or that there's no contextual effect. Doesn't matter when you're 84. After you control for the fact that you're 84, everybody's in the same place. Me and Mimi are on the same path. That's what that would mean. Well, her path is over, but you know.
I think I'm a little confused on why there's a quadratic term on the beta 0 line for level 2.
This one is necessary to turn the quadratic age effect into purely longitudinal. This one is also necessary to fix this term right here. It's used in two different respects.
Okay, well then now I'm confused. Okay.
About this one?
No,
Or-
the one that you were just talking about in terms
This.
of fixing this one. Yeah.
Mhm. So without this term, this is a cross-level interaction between the parts of age. It assumes that baseline age moderates the cross-sectional age effect and the longitudinal effect to the same extent. Equal moderation across levels. So this allows differential moderation at the between level as a contextual effect.
I don't think it's clicking for me. The first thing you
Fair.
said of like, we have both a linear, on level 1, we've got a linear effect and a quadratic effect.
Mm-hmm.
That makes sense to me why we would need it. So I think it's actually gamma 1, 1 that I'm confused about.
Yeah, so we would still need this quadratic effect of age at baseline, even if this weren't here.
Okay.
We would need it because of this cross-level interaction. Okay,
I'm still not following.
I know, it hurts, it hurts. All right, okay, let's see. Nathan, do you have the same question or you have a different question?
No, it's related. This is random intercept with fixed slope because we don't have a random effect in the level 2 side of things, right?
Yeah, there's no random slopes, only a random intercept thus far.
Would it mess things up to add a random effect, or is that coming later, or are we not able to do that?
We are going to do that, but we're not doing it yet.
Okay, so that is allowed, it's just we haven't done it yet.
It is allowed, and it will
Okay.
happen. It will happen, maybe not today, maybe it will happen Thursday or next week, but it will happen. It's in here at least. Okay, so hang on, where'd my thing go? I lost my, okay. So let's say this is essentially what I have here, level 1 age and level 2 age. So like two parts of age, so to speak, where this one has between plus within, and this one only has the between. Okay, so if I want to examine how the effective age varies as a function of some other variable, let's just call it P. I'm out of letters here for predictor. Okay, so if I have an interaction with level 1 age with P, then I'm saying the between part interacts with P just as much as the within part interacts with P. Okay, so that seems like a problem, right? So we agree on this, right? Equal moderation. So to fix it, I would need to add an interaction here so that this is the between by predictor interaction. Now you're controlling the between by predictor, this becomes within by predictor.
Great, thank you.
We're cool with that?
Yep.
Okay, now let me do the exact same thing. Like this. Now the moderator, which we just called predictor, is level 2 age. That's my cross-level interaction right here, is age by age. So for the same reason that we all just agreed, I got to put level 2 age here, which leads me to a quadratic effective level 2 age.
Great, thank you so much.
You're, no problem.
So, Lisa, if we magically were able to have a study where we were able to have everyone start at the same age,
Yeah,
then this would not be an issue.
that is correct.
Okay.
Yep. This is an issue in designs where people enter at a different point in the trajectory. So whether it's a trajectory of a disease process, time since birth, time until death, relationships. So like if you study relationship satisfaction, let's say that you're studying it in couples that are married. Did their relationship start the day they got married? Not unless they're on a reality show, I think. Typically there's, you know, a relationship building process, and then perhaps there's some interval in which they decide they want to get married or not. So like if you were going to study relationship satisfaction, time zero is whenever you started dating that person, or you agreed that you were dating, or whatever. Same thing with studying, like, you know, trajectories of divorce. Like maybe time zero is when you eventually got divorced and you look backwards to see patterns that would have led up to that. And it makes more sense to think of that way. But whenever people differ in the timing of something, to where there's cross-sectional time differences and longitudinal time differences, that's when this is a thing. More generally, whenever you have a level 1 predictor that has systematic level 2 variance in it also. That's the more general concept. Okay, so we're okay with the level 2 quadratic to unsmush the interaction. And by the way, this is not something a lot of people understand. I've had to correct multiple papers that are supposed to be tutorials on multi-level whatnot who mess this up in the paper. Either as an editor or as a reviewer. I'm in charge of quality control. On my tombstone, it will say, "She died. She gave her life to preventing smushing." That's what it will say. Okay, so to recap, this linear effective age gets unsmushed, controlled for the cross-sectional additional piece by this one. The cross-level interaction between the pieces of age needs the quadratic to unsmush it. And even if this cross-level interaction weren't here, this quadratic effective age needs the quadratic effective age to unsmush it. So they all map onto each other in terms of why they're here. I could have made this model even more complicated, like allowing moderation of the quadratic term, but at some point I had to, like, you know, stop and write it up and turn it in, right, as I tell you. Question?
So gamma O1 is going to tell us whether or not
No, not
random
two, huh?
intercepts are affected by baseline age.
This gamma O1 is going to tell us that. The one that I just fixed, which is supposed to be gamma O2, is going to tell us whether there's a quadratic moderation of age. So does the effective age on the intercept level off or change directions? So in the same way that we can have quadratic time varying age, we can have any kind of nonlinear function for a time invariant predictor as well. Yep.
Is this going to take us to unbalanced issues?
Unbalanced.
Unbalanced occasions.
Well, these are unbalanced occasions already.
Okay. Is this the secret that we didn't learn last semester? As like unbalanced data.
I hide a lot of things from you guys, so you're gonna have to be more clear as to what secret you're referring to.
Well, because like I know we didn't touch like unbalanced data last semester, I don't think. So is this how we would address that, or is that a different unit?
So the time component of this study, let me go back to the time model for a second. Time is also unbalanced in this case because it was supposed to be every 2 years, but it didn't exactly end up being every 2 years. Like for some people, it's like 1.9 and like, you know, 3.6 or whatever. So this time being unbalanced does not affect the idea of that it only represents longitudinal. It just means that there's multiple potential time values that are individual specific. But you're right that you did not see any examples of unbalanced time last semester. And that was usually in part because I was trying to show a V matrix of what everything looked like when it was put back together again, and that requires balanced time to show like that there's only one V matrix basically. Otherwise there'd be each person gets their own.
Oh, okay, that makes sense. And I know, yeah, I think I was, unbalanced time is still kind of elusive.
Unbalanced time
concept.
is like everybody has a different set of potential time observations,
Okay.
is the way I would think about it, as opposed to it being like a cross design where everybody's at every time exactly.
Okay. That makes
And
good sense.
yeah, and comment in the chat, does the Z matrix allow for unbalanced data? Yeah. So the Z matrix holds the values of the predictors to be given random intercepts and slopes. And so then your slope applies to whatever times you happen to have, because it generates a continuous function of heterogeneity of variance and covariance across time. Okay, an inadvertent review, that's what we're doing here. Just, little things here. Okay, so yes, these are both unbalanced. The difference is that age contains cross-sectional information, whereas that information has been stripped out of time to be purely longitudinal.
Lisa? So in this context, we will be using those contextual effects to see if after controlling for age, there are cohort effects.
Yes, exactly. After controlling for how old you currently are, to what extent does it matter when you are 84? Okay. That's what we're going to see. So we have then, those are my two level 1 terms, age and age squared. I have my two level 2 age and age squared for age at baseline, and then I have a cross-level interaction between the two parts of age. And there's no random slope yet. So I have 3 sets of estimate statements right here that I'm going to deliberately skip for now, but I'm going to come back to them. I'm doing the same thing with respect to saving information for likelihood ratio tests. I'm doing a likelihood ratio test to examine the contribution of these 3 new fixed slopes. This is the first time you've seen me do this. I'm doing a likelihood ratio test on the model for the means, because this is an overall, does cohort matter, is answered by these 3 slopes together. I could have done a multivariate wall test, but that is the point at which R stops agreeing sometimes with the other packages, and so for the sake of making everything match, I'm doing a likelihood ratio test. I'm allowed to do that because we are using regular flavor maximum likelihood. You can do any kind of nested model comparison in regular flavor maximum likelihood. And that, by the way, that is not a thing other people say. Likelihood does not have flavors. That's just the way that I talk about it. So don't write that in your papers. You can write smush, though.
We could make it a thing if we did that.
I know. I put smush in the index, and I put it in my papers. And whenever I see it in other people's papers, it makes me really proud. Like, I did that. Yeah. It's happened by accident. It was just like one day I was trying to find a way to explain it, and I kept making this gesture, and like they smushed together. And it was at a workshop, and so then there's people who were giggling, and I'm like, what are they laughing at? And I found out that the term smush has a completely different definition in the context of Jersey Shore, where they have something called a smush room, and that's all the further I'm going to go down that hole of, that rabbit hole of information. So I didn't mean it that way. I did not know that was a thing. All right, so, and then in our same idea here, we've got our 2 squared terms, our 2 squared terms at level 2, and our cross-level interaction. So in the output, I note that both the intercept and the residual variance were reduced relative to the age-only model. Now this should be a little bit surprising. The terms that I added are level 2 terms. But this one right here doesn't have a random slope to explain, so it has to explain residual. So that's why you do see the reduction in the residual, at least in part due to that. Okay, now the question, do we have cohort effects of age? Yeah, we do. These 3, all of them matter. So now my intercept. This is for somebody who's 84, for somebody who started the study at 84, specifically. So now my growth curve here is conditional for someone who started at 84. That is their trajectory. They start out at 9.4. They initially increase. But that rate of increase slows down and eventually turns over into the other side of the U. So after controlling for baseline age, the time effects have the same, or excuse me, the age effects have the same pattern as the time effects did. Not a coincidence. Before, the growth trajectory was assuming everyone was on the same trajectory without cohort effects. Now, these are relying only on the within level information because we have controlled for the cross-sectional between level information with these terms. Question or stretching? Stretching. You have a question. Okay.
So when you say that, that's why we literally see the same values, or pretty much the same values for those estimates as we did in Model 1B.
Yep.
For time and time.
Yep, and here's the punchline, because we're running out of time. We'll get to the punchline next time, but I have the two next to each other. Yeah. Here's the punchline that we're going to end up with. Here's the model we're looking at right now. Here's the model with time in it instead. These models are likelihood equivalent. The difference, and this is why, again, I have a job, different variables at level 1, same slopes. Same variables at level 2, different slopes. I know. So yeah, after controlling for cohort, what age at level 1 has left to do is the within part, the longitudinal part, to be time. And that is why, whether you have time as your level 1 variable or age, once you control for between person differences in age is immaterial. Both of these models are equally developmental or theoretical. If you forgive the quadratic, that is. That part's a little, questionable, but. So the difference is in what the context effects mean in this case, or the total effects mean in this case. Can we do maybe one of them? Let me go back to where we were. This one, am I here? Yep, this is where I was. Okay. So the intercept is for an 84-year-old, for somebody who started the study at 84. Otherwise known as time 0, right? If this is for when you're 84 and you started at 84, that is the definition of time 0. It works out to be the same. This is the slope at 84 for somebody who, other one, for somebody who started at 84. So this is the slope at time 0, essentially. If we do this one, given the interaction with time varying age, this applies to when time varying age is 0, so this is at 84. For every year older you are when you start the study, at 84 you do worse.
Can you say that again? I'm sorry.
Yep. For every year older you are when you start the study, you do worse at age 84 by 0.58. And the quadratic working with it, both of these are intercept moderators. Baseline age and its quadratic. What pattern is that?
More negative.
More negative, yeah. So there's a bigger effect of when you started in the older people. If you started at 85 or 86, that quadratic kicks in and it makes the slope even more negative. The scores initially increase at age 84. What pattern is this? That's a more positive. The scores increase more at age 84 in people who started older. And good luck writing a discussion section, basically, or a results section. I got a picture, though. Picture's coming after we add some random slopes. I got a picture for this. But the point of the story, the fact that baseline age has something to do, that it's not 0, these are functioning as contextual effects or cohort effects. They are allowing differences in the trajectory as a function of when you started. That means it is not okay to smush the effects of age together. It does matter when you started. How old, when you were 84, not just that you were 84. All right, 143, which means it's wrap-up time. Questions or things you want me to say again before we adjourn for today?
So, as a brief discussion, like after controlling for contextual effects, the effect of time varying age is blah, blah, blah. Is that how you would say it?
Yeah, because after controlling for contextual effects renders these two effects of level 1 age purely longitudinal. Because we've controlled for the part of them that was cross-sectional by sticking in these additional terms. So what's left is longitudinal. And that's why these end up being the same as if you had just put time in there, because time is only longitudinal. Okay, anything else for today, garbage day? All right then, thank you for being here. I hope to see everybody Thursday. Let me know if you need anything. We're going to pick this up on Thursday. We're going to do the homework 1 discussion, and that might segue into next week too. We'll see. So I'll let you know when I have new stuff available for you, though. Deal? All right. Adios. See everybody later.
Everything's always